start streaming. All right. So what we'll do is we're going to go back to YouTube and watch the Hungarian dance. Hungarian bubble sort. Okay. And here's the one. Theater mode. Okay. But we need to use it. On the side, I'm going to write down the numbers. Enjoy the dance, right? Yep, but you're only comparing between neighboring elements. Okay, so that's one thing that we can observe. And it's always going from left to right. Okay? And then the other important part is after the first pass, after we go all the way from left to right, the next pass is not going to end with A bracket 9. It's going to end with A bracket 8. You will actually see A bracket 9 to turn her back when this is done. So that is significant as well. There's no exchange because it is already in order. But you can see how 8 and 9 are both turning their backs. So this time we will go down to A bracket 6 and 7, and then it will stop. Visually, you can also see how 7 is moving down the list. Okay, the maximum of this portion is just moving all the way down to take its place where it's supposed to be, which is A bracket 7. This time only 7 turns back. Focus is, we only compare neighboring elements of the array. It's going from left to right. For the iteration, now it's back. That's it. Okay. All right. Yeah, that reminds me of the early day video games. You hate that sound. Is it Falcon? Or your spaceship blowing up? Yep. Okay. So I wrote down the numbers. Okay, on the side right here. So we got 3, 0, 1, 8, 7, 2, 5, 4, 6, 9. Okay. So now the question is, well, do we know how to do this by hand? Because you can't really write an algorithm to do something if you don't know how to do it yourself. It is only after we know how to do it ourselves, then we might have a chance of actually doing it, using a program, using an algorithm. So, okay, so now if we were to replicate what the Hungarian dancers did, okay, so the first thing they did was to exchange the 0 and the 3 because they were out of order. So now they're in order. So we'll do it step by step. Okay. And then the 3 and the 1 compare, and they were out of place as well, and those two also exchange their position. So then the sequence becomes 0, 1, 3, 8, 7, 2, 5, 4, 6, 8. Oops. And then after that, the 3 and the 8 were compared. They were not exchanged because that's in order. So the next one looks exactly the same as the previous one. There's no exchange. And then the 8 and the 7 were compared, and they were out of order, and they were exchanged. So the next one, so those two got exchanged. So 7, 8 became like that. And then we compared the 8 and the 2, and those were out of order as well. So now we have 0, 1, 3, 7, 2, 8, 5, 4, 6, 9. And then we compare the 8 and the 5. You can probably see that now it's going to exchange because the 8 is the largest element of the entire array. So that's going to get, quote unquote, pushed down to the end of the array. Because in every single comparison against any other element, it's going to be the one that's bigger, which is also automatically going to trigger the exchange operation. So that's why we see the 8 basically being pushed down all the way to the end.
Question.
Yep.
Why would the 7 and 2 not get exchanged?
The 7 and the 2 were not exchanged because the 2 got into that place because we exchanged these two.
Right, so if it goes back to the array on
We don't go back. You keep going from left to right until you get to the end of the array. Okay? So now we get to here, the 5, and then the 4 and the 8 got exchanged. And then the 6 and the 8 got exchanged. And then we compare the 8 and the 9. The 8 and the 9 are in place already. So in the video, both 8 and 9, turned their back, which basically means those two elements are now done. The question is, how do we know that those two elements are done and the next pass can go from the beginning, but we can stop with the position where the 6 is. So that's the question. How can we decide? How can we determine that?
You put a max counter.
Hmm?
You put a temporary variable that holds the maximum value that you've seen so far.
Okay. And how is that?
If the current values that you're switching,
Uh-huh.
say you encounter number 8 early on in the thing,
Mm-hmm.
so chances are any of the next numbers are going to be lower than that. But if you see a number that equals to 8 or a 9, that means if it sees a 9, it gets updated into that was held by 8. But if you see an 8, then it knows that you previously saw an 8 and there's nothing more than an 8.
Well, we know one thing for sure. We know that the last element is going to be okay. After the first pass, whatever is the maximum is quote unquote sync all the way to the last element. We know that much, okay? Because of the exchange mechanism, the largest element is going to be at the end of the entire sequence, of the entire array. The question is, how do we know that 8 is also in place in this particular case? So yep.
Maybe 8 is in place of the bar of
Mm,
The number of places of 8 equal to bar 8 bar.
well, but it's not the last element. 8 is the position of 8 is actually not the last one. This is our last one. So knowing that we can stop with this one, in the next pass is okay. But how do we know that we can stop with this one too? How do we know this one is already the correct value at the right place? That
Place is the number of bar in a bar minus 1.
Well, we'll just make a note here, okay? So we'll say, how do we know this is in place? Okay, so we'll just leave that question. Okay, so the next pass, which means the next time we go all the way back to the left hand side and run to the right hand side. So in that case, we have 0 compared to 1, no switching. 3 compared to 7, no switching. But 7 and 2 got switched. So the next one has 7 and 2 switched, like that. And then we have 7. 7 is the maximum we have seen so far. And in fact, it is the largest of this portion of the array. So that's going to get pushed all the way down by exchanging with values all the way down. Okay, and then get pushed down one more. So the 4 and the 7 got exchanged. And now the 6 and the 7 also got exchanged. Is that okay? So do you guys remember in the video, did 6 and 7 both turn their back? Only 7, exactly. So the question is, how come it knows that this time, but 6 is actually at the right place too as well, but it doesn't qualify and turn its back. Yep.
I have a question. Like you said earlier, if 9 was the biggest number, it would have to move all the way up and go through all of them. But because 9 was already at the end, wouldn't that mean because 8 got, by the time it got there, is the only one, 9 couldn't move because it was already the greatest, so that's how you know 8 would be also done. I'm just saying for this example, because 9 was already at the end.
Mm-hmm.
So
As a counterpoint, if you had another 9 array,
Okay, so if we do not optimize and we just decide to run all the way to the end, would that be incorrect? In other words, even in this particular run here, we know that we could stop here, but if we do not stop and we say compare 7 to 8, well, they don't have to exchange, and then we compare 8 to 9 and say that they do not have to exchange, is that incorrect? In other words, does it give us the wrong result? It does not give us the wrong result. It's just spending extra time to do something that we do not have to. Okay. All right. So, but just going through these 2 rounds, okay, we will call this one pass. We'll call this the second pass. So now the question is, how do we structure the pseudocode so that we can capture that logic? Yep.
Does it maybe only check for one position per pass?
Okay, for each pass, it is starting all the way from the left-hand side.
Right, no, I get that. I mean,
Right.
I mean this particular thing we're talking about where it, basically if they turn their backs, like,
Mm-hmm.
does it only check for one of those per pass? Is that why 7 turn and 6 turn?
Well, we know for sure we can back up 1 for each pass. So for the first pass, we know 9 has to be in place after we run the entire algorithm through. We don't know why it knows 8 is also in place, because it depends on which version, which algorithm, which bubble sort algorithm you use. But the simple one does not know. The simple one cannot make that assumption that 8 in this case is already in place. So the second one would actually compare the 7 and the 8 and know that there is no need to exchange those two. Then it would conclude that 8 and 9 are both in place. And then the next pass is going to exchange everything all the way down to the 7 and so on. So the Hungarian dance video is using an algorithm that tracks more than just what a basic bubble sort algorithm is going to do. Okay, so that logic, we don't know, how they figure it out yet. Okay, but what we know for sure is there are multiple passes, because we have one pass like this. This is called one pass, and then we have another pass like this one. This is the second pass. So what do we do in each pass? That's the first question. And then the second one is, how many passes do we need to do before we stop? So there are two questions here. So let's deal with one pass at a time, okay? So we'll deal with this pass here, and then we say, how do we specify the logic to perform that pass? Okay, that's the question.
I think as long as the numbers of the array, it's 10 numbers, 10 times.
Okay. So let's go ahead and try to implement just one single pass. So we'll implement this as a subroutine. Define sub. We'll just call that one pass. Okay. And define sub. So don't copy anything on paper, because I'm going to kind of like put things in it as occasionally. We know that for sure we need a pass by reference parameter for the array itself, right? We know it has to be passed by reference, not only because we're dealing with C and C++, where arrays can only be passed by reference, but also because we are changing the content of the array. If you're not passing something by reference, you're changing a copy of that thing, so you're not going to affect the original thing. So we know A, or the array, has to be passed by reference. So we say that this is A, which is an array of integers. What else do we need to pass? Well, we need to pass where to stop, because if you watch the Hungarian dance, it has the numbers to the end or the right-hand side to turn their back, and those never got compared again. They were not processed again. Okay, so we need another number to indicate when do we stop. Okay, so this one we can pass by value, because it really is just a number that we need. We're not going to change it. So we have by val n, or we can sort of call it end. No, end is a bad name. Last. There we go. So last is just an integer. It is the index of the last element that we need to compare. Okay. Do we have anything to return? So that's another good question, is do we have anything to return so that the caller can decide on something? What do you think? How do we know when to stop? Well, we can stop when everything is sorted, right? So how do we know when everything is sorted? So I'm going to say here, return type is something, okay? I know there's something we have to pass back to whoever was invoking this subroutine, but I don't quite know what it is and how to use it yet, okay? So we'll just put a question mark here. We'll go back and fill that in later. We need some local variables, okay? We for sure need a local variable to determine which pair of numbers are we comparing. So local variable I and I plus 1 will be the indexes of the two elements that we're comparing, and determine whether they need to be exchanged. Okay. So now we'll go ahead and start to write the subroutine, or try to write the logic of this code. So the first thing is this going to be, okay, remember there are three main control structures that we can use: a sequence, a conditional statement, or a loop. Okay. How do you know this is a loop? Okay. Okay, so you guys somehow got a sense that this is going to be a repetitive process where we're doing something over and over again. Okay, fine. So we'll do it as a loop. So we'll say loop and loop. Now this is not in pseudocode, because once again, we don't know whether it's a repeat until loop or it is a while loop. Okay, so until we know that, we will just say this is some kind of a loop. But every time you have a loop, you have to say exit when something, right? When do you get out of the loop? So in this case, we get out of the loop when we have processed all the way to the index called last. Okay? So we say, when I is no longer less than last. So when I is greater than or equal to last, we can get out of the loop. Question?
I feel like you would also need a variable for a flag.
Yep, we do. But we'll deal with that later, okay? So we can only work out so much detail for each time. So we're going to take this code, copy, and paste it. So now in the next iteration, we try to specify more detail. When you have I as a local variable, it starts with an unknown value. So that means it needs to be initialized somehow, right? So now the question is, how should I initialize local variable I when I and I plus 1 are the indexes of elements in the array to compare? What is the first one? 0. Okay, well, that's useful because now we know I has to be initialized to 0, okay? And do we know what we are really doing per iteration? Well, remember the dance, okay? So we're going from left to right, which means the indexes is going from 0 to larger values. But we are also observing that the dancers that are actually doing something is a particular element in the array and the one right next to it, okay? So what we can tell here is we can see that a bracket I and a bracket I plus 1 are the two elements that are of interest to us. Exactly what we're doing with these two, well, we can deal with that later, okay? At the end of each iteration, we have to prepare for the next iteration, which moves to the next pair of dancers, right? So that means what do we need to do to I? I has to be incremented, so I gets I plus 1. Okay, so we don't know what we're doing with this, okay? We don't know what kind of control structure to use. We don't know exactly how we want to compare those, but we know this is what we need to do. Is that okay? All right, so we'll call this another iteration. So we are starting to fill in more and more details. All right, so in this particular iteration, we kind of have to be a little bit more specific and say, what are we doing with a bracket I versus a bracket I plus 1? We know we're comparing, but there are 6 comparison operators: equal to, not equal to, less than, greater than, less than or equal to, greater than or equal to. So the question is, which one is of interest to us? We know equality is not of interest to us. We're not comparing whether they're the same or not. So what are we comparing for? Greater than. Okay, very good. Because when they are less than, we don't do a single thing. We just kind of leave them alone. There's nothing to do. But when a bracket I is greater than a bracket I plus 1, then we have something to do. Okay, so we use a conditional statement and say that, well, there's something to do when a bracket I is greater than a bracket I plus 1. Okay, but we are not going to specify in this case because I think it's really great that we figure out that this is a conditional statement, so we call this another revision. All right, so in this particular revision, we'll go in and say, well, do you remember what the dancers did when a bracket I is greater than a bracket I plus 1? The exchange position. Okay, well, to do exchange position, we kind of need to use a temporary variable, so we will use another local variable here. So local t as a temporary variable, and we'll just repeat that sequence, which is t gets a bracket I gets a bracket I plus 1, and a open bracket I plus 1 close bracket gets t. That is a very typical sequence of instructions or statements to exchange the values of two things. It just turns out that the two things that we want to exchange are elements in an array. Okay. All right, so that's kind of cool. We're now getting closer and closer. And then what else do we need to do? Well, as far as one pass is concerned, this is all that we need to do. But there's one thing, there are several things that kind of stands out in this case. Do you remember the last pass? All of the elements turn their back at the same time. I think there were like 5 of them all turning their back at the same time. How do you know it knows that, oh, we don't need any more passes? because no exchange took place. Okay, nothing was out of place as we scan from left to right. Okay, so that seems like something that's useful to keep track of. Okay, so now that we know that it is kind of useful to keep track of the exchanges, like when did we do the last exchange, then we'll ask the question of, should we represent it? How should we represent that? Should we, huh? Flags. But when you use the word flags, it implies that we are dealing with a Boolean, something that's either true or false. So in that case, you're basically suggesting we use a single Boolean variable, local variable, to remember whether an exchange took place or not. But we cannot differentiate how many exchanges, nor where was the last exchange, right? Okay, so it might be more useful to remember when was the last exchange. Wouldn't you think that? Okay, so we'll go ahead and try to use another local variable to remember that. Okay, so we'll say last exchange index. Okay, teacher. Now, because this is also a local variable, it also needs to be initialized before it is used. So the question is, well, how should I initialize this? Because it is possible that the first two elements got exchanged where I equals to 0. So initializing this to 0 doesn't seem to be very helpful, okay? Because I need to differentiate between the cases where the first pair was exchanged as opposed to no exchange took place. So I need a particular value to tell me that no exchange took place. -1. So anything out of the range of valid indexes can work, and -1 certainly will work in this case. So now we'll initialize last exchange index to -1, which is quote unquote an invalid value. And then every single time we have an exchange, we're just going to be updating that too. So last exchange index is now getting the value of I. Okay, so we are basically just tracking where did we do the last exchange, because that seemed to be of interest to us. Is that okay? All right. Is that okay? Okay. Now we have another question to answer, because I was only using loop and loop, but the question is, should I use a pre-checking loop or a post-checking loop? In other words, should I do a repeat until, which is a post-checking loop, we perform the operation first, or should we use a pre-checking loop, which means we check the condition first? Pre-checking? Okay, so under what circumstances would you not perform a single iteration? When there's nothing to compare, right? Okay. Yep.
I would say post-checking.
Well, the answer is it depends on the caller. It depends on what value are you expecting in last. So if last can be, let's see. Actually, let me last. This has to be last -1, cannot be just last, because we are comparing to the neighboring neighboring member element of the array. So, what was I talking about? I lost track.
Like if this would be a pre-checking loop or
Right, pre-checking loop versus post-checking loop. So you can do it in either one, okay? It all depends on what the caller is going to do. Do you expect the caller to give you a case where last is just 1, where you don't have to perform a single iteration? Okay? If that is not going to be expected, then you can use a pre-checking loop or post-checking loop. Is that making any sense? So I'm going to use a post-checking loop here, assuming the caller is going to do the reasonable thing and make sure that we have at least something to do. So we'll turn this into a repeat until. Okay, which also means the caller cannot give me some value for last that is unreasonable. Is that okay?
What do you mean unreasonable for last?
Like last cannot be 0. Okay, and last can last be 1? If last is 1, and this is the condition to stay in the loop, then 0 is less than 0 is going to be false. So last cannot be 2, cannot be 1 either. Last has to be at least 2. Okay, let's look at the other version. Okay, so we're going to compare two versions here. I'm going to open up another window, so this way we can compare the repeat until implementation as opposed to the while do version. So we'll take this and paste it here. In this one, we're going to use a while do. So we have while. Now remember, in the while, you have to reverse or invert the condition. So if the exit condition is when I is greater than or equal to last minus 1, then the while loop has to say while I is less than last minus 1. Okay. So repeat is replaced, it's gone, and then until is replaced by and while. Okay. And they're off by 1 line. Oh, they're not off by 1 line. I just displayed them off by 1 line. Okay. So when you look at this loop here, when do you think you have no iterations to perform? Since I is initialized to 0, when last is 1, we have no iterations to perform. But when you're looking at the repeat until loop, we have 1 iteration to do, because it will perform the operation before it has a chance to get out of the loop. So that means, if you look at this code, last has to be 2 or more to perform a single iteration. Is that okay? All right. Okay, so we just have to kind of keep track of, what value is reasonable for last from the caller's perspective. But we have one more thing to do, because we don't know what we are returning. Remember, that question mark return type, what kind of value are we returning? Now we have a pretty good idea of what value we are going to return. We're going to return an integer. And what integer do you think we're returning? No. We're going to return something that changes depending on the array. And what do you think that is? Okay, first of all, do you think returning I is going to be useful? Why is it not useful to return I? Because I is just going to be last, right? So why would I want to return a value that was passed to me to begin with? That doesn't make sense. So I really should not be returning I. Should I return t? What is t? Local variable t. What is that used for? It's for exchanging things, right? What if there's nothing to exchange in this code? Then t becomes uninitialized. And then I will be returning an uninitialized variable, which basically can be any value. That doesn't seem to make sense either. Last exchange index, exactly. So we're going to return last exchange index in this case. If it returns -1, that means, we did not have to do one single exchange at all. But what is that telling us? What is that telling the caller when we did not need a single exchange? Everything is already sorted. Everything is in order. Excellent. Okay, so that seems to be useful, right? Okay, so we'll keep this around. And I'm going to use this window to specify bubble sort itself, which is going to make use of 1 pass. Okay, so this is define sub bubble sort. And bubble sort definitely needs an array as a parameter, because otherwise, what are we sorting? So we need an array of integers to sort. And we know it's going to make use of one pass because otherwise, why did we write that subroutine called one pass? So we know somewhere in here we're going to invoke one pass, and every time we invoke one pass, we have to specify A, which is passed to bubble sort as a array passed by reference, and we'll just pass that reference along to one pass. So we know that one has to be passed. We do not know yet what we're going to pass to last as a parameter. Okay, so we will decide it later. The other thing that we also have to decide in bubble sort is the overall control structure of bubble sort. Do you think it's a sequence where we just have to do a whole bunch of things once and we're all done? Or do you think it's going to be a conditional statement? Sometimes we do this, sometimes we do that, but it's still a one-shot thing. We just have an option to choose somewhere down the line. Or do you think it's going to be a loop where we have to do something again and again and again? Of the three, which one do you think we should use? It should be a loop, because in the Hungarian dance, we have to perform multiple passes. Even though the first pass, had the longest run, the second pass, didn't have to involve as many elements, and then the third pass is even smaller, there were multiple passes. Okay. So, and we also know that each pass is going to perform one pass. Okay. So we have loop, because I don't know what kind of loop I want to perform here, and then we have end loop here. But when do we exit?
When it returns -1.
Aha, very good. So when one pass returns -1, we know we're good. Okay. But doesn't that mean that we need something to store that? Okay. So either that, or we can utilize the value of the invocation of one pass directly in the condition itself. So we can do one or the other. For the sake of clarity, we'll just go ahead and do it the kind of longer but more clear way. So we'll have a local variable that keeps track of, I'll call it x here, okay? So x is an integer, and the only job of x is to store the return value of invoking one pass. And then we'll just say that when x is -1, when x is -1, we can get out of the loop. Is that okay? But we are still missing something, right? Because, you guys cannot see the entire thing. So I don't think we need to look at the the table of the values. So now we can just focus on the algorithm. But we're still missing something here. What are we going to do to specify last? Bar A bar initially, okay? But remember, we don't have to end at the very last element every single time. If you watch the Hungarian dance video, the dancers who have turned their back were never compared again in the next pass, right? So that means last is whatever we pass to last has to be a value that is going to change. Okay, but whatever that value is, we know that it has to start with bar A bar -2, not -1, but -2. Okay, so we have another local variable here to keep track of that. Okay, so we'll call this. I don't want to call it last, because it is going to be confusing. So we'll call this. We'll call this W. Okay, and we know this W has to be initialized to bar A bar -2, not bar A bar -1. Because if we make this bar A bar let's see here. Yeah, -2 is correct, because if it's bar A bar -1, then W becomes the index of the very last element. So when we pass that W into one pass, then when I is last -1, it will still go back and perform one last iteration. When I is last, or bar A bar -1, and then -1, that would still be that would be correct. Okay, so bar A bar -1 turns out to be. That is correct. Okay, -1 is correct. It's the index of the last element that we have to compare. And then because of the way I structure this conditional statement, it will make sure that I do not go back to compare again when I'm about to go out of the bound of the array. So that's fine. That actually does work. Okay. So having W initialized the way it is, we kind of know that this is going to be W, at least the first iteration. But then we have to ask the question, how are we going to change W for the next iteration? Well, do you think there's a relationship between X and W?
Yes, because if the value of x is not -1,
Mm-hmm.
we change the value of w.
Yep.
How would you?
Okay, so W tells us where we are supposed to stop, the index of the last element to be involved, right? So that means that's telling us where to stop, excluding the dancers that have turned their back. Okay. And so now when we go back, do we know why? We know how many dancers can turn their back after one single pass. You want to watch that video again? I have to chop that into sections because the very last pass, if you remember the very last pass, we have like 5 dancers all turning their backs at the same time because there were no exchanges. Nothing was out of order. Okay? Yep, go ahead.
Well, I was just about to say what you just said, is that it's related to the amount of exchanges, but I don't know really how.
So where we did our last exchange helps determine how many dancers will be involved in the next pass. Okay? All right? And that value is returned to us as last exchange index from one pass. In other words, that is now that's given to us as X. So given X is telling us how far we had to go, what was the last exchange in that one pass, and W is telling us when the next pass, what is the extent of the next pass, what do you think is the relationship? How do we set up the next W? Well, we know it has to do with, it's related to X because it's going to get closer and closer to 0. Hmm?
Subtract x from the amount that
Nope.
fixed to 0?
Nope. Because X is still an index. Because if you look at how the way last exchange index was assigned, it was basically I. It was basically telling us, what was the index of the last element that got exchanged, right? Okay, so given this algorithm, okay, now we go back and say, okay, do we need a loop, and loop, or do we need a while loop? I think it's pretty clear. Because if you turn this into a while loop, what was the initial value of x? X is a local variable. It doesn't have an initialization. So if you turn this into a while loop, it doesn't make sense. So it has to be a post-checking loop. So we'll turn this into a repeat until loop. Because x only got its value from here, and this is the one thing that we have to do, or one of the things that we have to do repetitively. So that means we have a repeat until loop again. Is that okay? So once we have this, we can give it an example to trace, or we can just try to do it by hand. Let's do it by hand, okay? So what we'll do is we'll do it by hand, but not only are we doing it by hand, we are going to use the same example that we saw in the video. because this way we can cross-reference and see if the behavior of the algorithm is going to match the Hungarian dance video. Because that's the objective, right? You observe something being done, you're trying to capture the logic of how to get it done. So now this is great because we have something to compare to. But in real life, sometimes you don't have a Hungarian dance video to go back and say, is my algorithm doing the same thing as the Hungarian dancers? All right, so we'll go ahead and let's see. This is bubble sort. This is one pass. These are two different pieces of the same program because one pass is called by bubble sort. And then what we'll do is we will look at the Hungarian dance data here. It starts off with this particular array. I won't do this trace in the spreadsheet because it's going to look very, very, very ugly. Okay? So we'll just do it on the side here. All right, so we'll deal with the first pass, okay? So we'll say this is first time calling one pass, okay? The first time we call one pass, what is last again? The parameter last is initialized to what? So if you look at this code, W is passed to last, and W is initialized to bar A bar minus 1. So in this case, I think there are 10 numbers, right? So last is going to be 9, okay? Last has a value of 9, I should say equal to 9. So now we perform the operation. I is initialized to 0, right? So we say I is initialized to 0. And then last exchange index is initialized to -1. I use the equal sign here instead of the assignment operation because this is the condition when we first start one pass as a subroutine in the loop. Okay. All right. So then we first compare these two, and they certainly need to be exchanged. So we perform this operation: 8, 7, 2, 5, 4, 6, 9. But when we perform this operation, because we involved an exchange operation, so as a result, last exchange index is going to be updated to 0. And also, because this is a loop, we have an increment of I at the end. I becomes 1 before the next iteration. Is that okay? So in the next iteration, because I is now 1, we are now comparing these two, and it says, yep, we need to exchange these two as well. So now it becomes 0, 1, 3, 8, 7, 2, 5, 4, 6, 9. And as a result, last exchange index is now 1. And then before, at the very end of that iteration, we also increment I. So I is now 2. Is that okay? And then we look at this, and we go like, okay, do we need to exchange the 2 and the 8? Nope, nothing is going to happen there. So I is incremented to 3 without changing anything in the array. When I becomes 3, then we'll be looking at these two, and we go like, yep, we need to exchange those two. So from here on, I'm just going to be super lazy and just copy and paste and then exchange those two. But as a result of this, last exchange index is also going to be updated to 3. Is that okay? It has to do with this code here. It has to do with in one pass. Yep, that's the one. Okay. So it has to do with in one pass. Right after the exchange operation, we also remember I as last exchange index. Is that okay? All right. So last exchange index becomes 3, and then I is incremented to 4. So we are now looking at the 8 and the 2, and we go like, yep, those two needs to be exchanged. So we copy and paste, exchange the 8 and the 2. 0, 1, 2, 3, 4. Yep, these two are the ones that are involved. Last exchange index is now 4. I is now 5. So now we are looking at 8 and 5 need to be exchanged. So, and then we exchange these two, 5, 8. Last exchange index is now 5. I is now 6 because we have the advance to the next one. And now we are comparing the 8 and the 4. They need to be exchanged as well. So we'll do the exchange first. And then we remember that last exchange index is now 6. Yep, go ahead.
Sorry, this is going back to your previous question that you asked earlier, why the last two positions are unchanged.
Mm-hmm.
Is it because the program knows that it didn't need to swap on the last?
Yep.
Okay.
Because you can see the property of one pass is whatever is the largest value within the range of indexes that I need to look at, that is guaranteed to push all the way to the end.
Yeah.
Yep. So if there's one thing out of place, we'll find it. Yep. So I is 7 now. Now we look at whatever is at index 7, which is this 8 again. So we look at 8 and 6. They're out of place. We have to exchange those two. So now we copy and paste again and exchange those two, 6 and 8. And then I become, last exchange index is now 7 and I is now 8. When I is 8, we are not done yet. Okay. Let's see.
You're still comparing it.
Well, in the Hungarian dance, the last two elements were never compared. Were they? No, they were. They had to be compared, because otherwise, there's no way we can actually know that it is already done. So we compare those two, and because they do not need to be exchanged, I becomes 9, and that will get us out of the loop.
Yeah.
The reason why that is going to get us out of the loop is I is now exactly last minus I minus 1 is greater than or equal to I minus 1. Last is 8, and so we should have stopped when I is 8 already.
No, that's true though.
Right. Okay, this is repeat until. Okay, so when I is 9, then 9 is greater than or equal to 9 minus 1 is finally false, and we get out of the loop. Okay, that makes sense. And what it's going to return is returning 7, because 7 is in last exchange index. So now the question is, does that make sense? Is 7 the index of the last element that we need to compare to in the next iteration? Which one has the index of 7? Let's count. 0, 1, 2, 3, 4, 5, 6, 7. So that is indeed representing the index of the last element that we need to involve in the next pass. So just by dumb luck, I got the algorithm right the first time. But the idea is the same, okay? It's the main idea that counts, and also then it becomes the idea of how do you test the algorithm to see whether it works or not. And you can see that I did everything basically by hand. I did not run it through the spreadsheet at all. I did not write a program in Python. I did not run it in C. I just ran the whole thing by hand. And I was comparing the behavior of this particular pseudocode to Hungarian dance, to the video, of all things, right? But that's useful because if you have something to compare this to and go like, okay, that seems to be the right way of doing things, then it's going to help. So it's 7 o'clock. We're going to take a 5-minute break, and then we'll come back and continue with more of this stuff. start here, just to give people more time to come back. So there was a little discussion outside about the future of AI, artificial intelligence. And so this is just my thought. The current direction that we are taking using deep neural net to learn how to do things from mostly just human interaction with things is not really AI, it is EI. It's emulated intelligence, not artificial intelligence. Okay, so that's just one thing. And then the other thing was I promised people who went out that I would explore the first movie that talked, well, TV series that talked about uploading human the mind, the human what consciousness onto the net, okay, so to speak. And the movie was a TV series. I kept saying movie, but it's actually a TV series. It was called Max Headroom. Okay, and you have to watch it. Okay, I'm pretty sure YouTube or somewhere has the full and the entire series. But the reason why it's called Max Headroom was because this guy was running away from something, and then he was driving on a motorcycle or something. But he hit the maximum headroom bar in a garage, and then he hit that. He lost consciousness. He was in a coma, and then somebody decided to upload part of his consciousness onto the computer. So the computer alter ego of this person is now called maximum headroom or max headroom. So, yep, we got plenty of these clips here.
Play one.
Still alive out there?
Good. This is Max
Nuclear waste.
They say that the pollution is being caused not by them, but by all the dead fish we have today in the sea.
This might be a remix.
Max! What I want to know is, why are the only funny lines on this show the ones...
No, it's actually a lot more than that. This is back before the internet became the internet that we knew, that we know now. So people were not really, even aware of, oh, you can move things around. But Max Headroom as an AI can move from one computer to another computer. So he's more resembling, a virus that we know of now than, back in those days, that concept did not exist. And also, when they were using this show, he was actually in televisions, because people did not, were not, computers were not popular. Okay, it's not like everybody has a computer or has multiple computers. So the only thing that the show did not really capture that we have now is wireless technology. That was not captured in that TV series because that's way, way, way before wireless technology or wireless networking became reality. But it's kind of a neat show. Yep.
I mean, I guess it's not exactly a good example of like wireless networking, but like one of the other things that Max Headroom is famous for is there were hackers that attempted to and succeeded at broadcasting some footage recorded using a Max Headroom mask with somebody who's presumably supposed to be one of the hackers in the mask, just like kind of speaking like insane sounding stuff. And it was the hack was to have that air for a little while on like national television. And back I think that was really effective because of it made people who saw it were really aware that information that is being broadcasted in any form can be compromised, things can be sent over by normal people who just have certain skills, which would eventually, would become the future of how computers basically are in our daily lives.
But it was a noteworthy TV series. Even by today's standard, it was actually kind of interesting.
They
Yeah, I have no doubt.
Seems to be now, but when I was like 4 years old, that wasn't.
So I'm older than you then.
That kind of reminds me of Johnny Quest.
Johnny Quest.
He would like upload himself into a computer
Johnny
and they would
Mnemonic?
go on these like weird adventures through cyberspace. But it was
No, Johnny Quest is different. Johnny Mnemonic, which is also starred by Keanu Reeves, okay, was another sci-fi show, and this time, he was a human hard drive, so he was used to smuggle information out. So that show was called Johnny Mnemonic. It's interesting because they were smuggling information, and he was hired by a resistance cell, right? And then the leader of the resistance cell was a dolphin in a suit.
Dolphin in a suit.
It was a dolphin in a suit.
I like that.
Yep. Now, of course, if you like dolphins, you have to like Hitchhiker's Guide to the Galaxy.
Yes.
Yeah, thanks for the fish.
Wait, that's a book, isn't it?
And movie.
And a movie.
And a movie.
And a BBC miniseries. Yeah.
Okay.
BBC miniseries is way better than the movie.
So we're gonna go back to the Hungarian dance example because I want to double check and make sure that the second pass is going to stop where it's supposed to. Okay. So now we go look at this and go like, okay. So I equals to 0. 0, 1 is okay. We just move I along. I becomes 1. 1 and 3 are fine, no problem. I equals 2. Oh, by the way, there's one more thing we have to track here. We have to track last exchange index, which is initialized to -1 before we get into the loop. Okay, so when I equals 2, we will be comparing 3 and 7. Those are fine. Okay. When I equals 3, then we have a problem because 7 and 2 are out of place. So when I equals to 3, that will trigger an exchange between 7 and 2. But at the same time, we also have to update last exchange index to become 3. Then I becomes 4 because we have the increment at the end of the loop. So we are looking at 7 and 5 out of place as well. So we exchange those two. So we exchange the 5 and the 7. Last exchange index is now 4. I is now incremented to 5. So we look at the 7 and the 4. Those two are out of place. Yep, exchange them. So copy and paste. Exchange the 4 and the 7. And then we update last exchange index to 5. I is now 6. So now we look at the 7 and the 6. Out of order again. Exchange those. Oops. There we go. Exchange these two, 6 and 7. And then last exchange index is now 6. And I equals to 7. Now the condition becomes false. Because last, as an input parameter, is also 7. 7 minus 1 is 6. 7 is not greater than or equal to 6. So we are done. Is that okay? So the last Hungarian dancer who got involved in this particular case is when I equal to 6, 0, 1, 2, 3, 4, 5, 6. So these two would be compared, but they are not exchanging. So what the return value in this case is going to be 6. And you can see how, okay, return 6 from this particular invocation, but you can see how 6 is less than 7. So we specify 7 as last as a parameter, but it returns 6. It's guaranteed to be one less than last, but sometimes it can be a whole bunch of less than that. Okay. So here comes the third iteration. So third time calling one pass from bubble sort, and this time we use 6 to specify last, and we redo all the initialization. I gets rewind back to 0, and then last exchange index is -1 again, which is basically saying nothing needs to be exchanged. And then we'll start the whole thing again. So we look at this, and we go like 0, 1 is fine. Okay, I gets incremented. 1 and 3 is fine. I gets incremented again. 3 and 2, well, we need to exchange that. So we'll exchange those two. So now we have 2 and 3. But at the same time, we have to update last exchange index to 2. And then we increment I becomes 3. When I becomes 3, we are comparing the 3 and the 5. That's fine. I equals 4. We compare the 5 and the 4. That is not okay because they need to be exchanged. So we copy and paste 0, 1, 2, 3, 4. So these 4 are now exchanged. And as a result, last exchange index is also going to be updated to the current value of I, which is 4. I is now incremented to 5. We compare the 5 and the 6. They're already in place. Oops. And then the I gets incremented to 6, and we're done. Because the input or our last parameter is only 6. So last minus 1 is 5. I is now 6. 6 is greater than or equal to 5 is false. So that's why we got out of the repeat until loop. Are we okay so far? Okay. So what is the return value this time? What value is one pass returning? It's returning 4. It's always returning last exchange index. So it's returning 4. All right. So now that it returns 4, this is the fourth time calling one pass. So we use 4 to specify last. And reinitialize all the local variables. I gets 0. Last exchange index gets -1. And then we copy and paste the array. It really is the same array, by the way, in the algorithm. So when I equals to 0, we compare the 0 and the 1. Everything is good. I increments to 1. We compare the 1 to the 2. Everything is good. I becomes 2. We compare 2 to 3. Everything is good. I becomes 3. 3 and 4 looks good. I is now 4. And we're done. So this time, what value are we returning? -1. So this is the time when we saw the first 5 elements. They all turned their back at the same time. So when the return value is -1, if you go back to bubble sort, not one pass, when you go back to bubble sort, when x is -1, we get out of the loop because the loop says when x equals to until x equals to -1. X is now -1, so we get out of the loop and bubble sort is concluded. Is that okay? So I have to be like super honest and tell you that before today, the bubble sort that I know of does not actually back up the next pass as much as this particular one. This one is more optimized than the one that I was planning to talk about. But because of the Hungarian video, we go like, that's not the bubble sort that I know, but it's kind of smart. How did they do that? How did they know when to stop? So as I watched the video, as I processed the numbers, that's when I started to incorporate that logic into the pseudocode. But is that process okay? I mean, did you guys see the process of how I reasoned out the pseudocode of the Hungarian dance? It was okay? Are there any questions about that process? Does that mean in the final exam I can show you guys another Hungarian dance and you guys will write the pseudocode for that? it's not about the time, right? You know, this is about exposure to problem-solving sessions like this one. Okay, and writing algorithm is not really something that can be taught easily. It's not like the syntax of a programming language. And by the way, what is the syntax of a programming language?
The specific words you would use to control functions.
The words, the order, the punctuation, where to use a semicolon, where not to use a semicolon, what parentheses mean, how are they different from square brackets, right? And so on and so forth. So they basically, it's the same thing as grammar in a natural language, okay? So how do you learn, the grammar of a particular natural language? Painstakingly, it's mostly memorization, right? It's mostly memorization. Now they can make it more fun, with that process. So watching soap opera in a different language and being interested and getting addicted to the series can help. Okay, so that would be a great way to learn Japanese because a lot of anime is a lot of fun to watch. Okay, we see a lot of heads nodding. But that's the rote learning part. Okay, but does that process teach you how to write your own story in a creative way? So you can write the next anime series that is really kind of cool. No, it does not, because it only tells you, by watching that sort of thing, you're learning the mechanical stuff. Okay, like in Japanese, the verb is the last of the sentence. Okay, so the ordering is different, and the way they use adjectives is different, the positioning is different, and so on. And you start to learn the words, what means, what baka means, and so on and so forth. That usually is the first word to learn in Japanese. Baka, It means fool. But it's not super insultive, it's just a little bit insulting, but not super insulting. At least from the context that I learned from watching anime. But the process of how you come up with a story is different, right? And it's the same thing with programming. By watching the video to come up with, so the first thing, okay, so let's kind of go back in time because I do want to show you the whole process. And I'm hoping that we still have that. This is the first thing that I captured, right? I watched the video. I captured the behavior or the abstraction of the Hungarian dancer. So what you're seeing from line 1 to line 10 is basically the video clip without the dancers. We are distilling everything down to just the numbers and the ordering of the numbers. And then what we noticed, from watching the video itself, was in the process of the dance, we noticed that there's a left to right kind of thing. That's the first thing we noticed. The second thing we noticed is we only compare to the next element. So we compare the 3 and the 0. They need to be exchanged. And that's something that we noticed too. In other words, someone who did not know anything about sorting algorithm or stuff like that would also notice exactly the same thing that we saw and go like, oh, okay, I guess they're changing position only if something is out of order. So that's how we gradually kind of capture the way of doing things. So from looking at the sequences like this and how we change the array from one row to another row, we came up with the algorithm one pass. But I didn't come up with one pass in one single, session. If you go back to the beginning of this slide here, okay, we came up with something that was far more vague compared to the last version. So I was only adding, logic step by step. And that's the way that I write algorithms, okay? Or at least mentally, that's what is getting processed in my head. Do I actually go through this process with a lot of intermediate representations of an algorithm when I write my code? Most of the time, no, okay? Most of the time, the process from here all the way to close to the end is all internal. It is completely inside my head, okay? But when you're starting out, you might want to do it kind of more explicitly. In other words, you just kind of spell out what you know has to be true, and then you try to specify more details as you go. Is that okay? But we also kind of notice one thing, I turned one pass into its own subroutine. In other words, I do not look at bubble sort as one gigantic piece of logic. I just break it apart and go like, okay, let's deal with only one pass. Now, why do you think I noticed that there's a concept of a pass by watching the video? Okay, go ahead, sorry. There's a visual representation, but which part of the video do you think gave me the idea that there are multiple passes? It happened more than once, exactly. So we saw, how the pair of dancers, kind of move in from left to right, and then they went back to the first part, and then they go again. Even though it didn't go all the way to the end, it was still kind of the same thing, right? And then they went back to the beginning again. So it repeated that like 4 times. There were 4 iterations of going from left to right. So that was what gave me the idea of, okay, let's not fix the entire problem. Let's just figure out how to do one pass. And that's how I made the subroutine one pass, just to do one portion of the algorithm. Once I figure out how to do one pass, then I go like, okay, so how many passes do we need to do? And how do I control when to stop for subsequent passes? Then I start to think about all of those things. And if you go through the logic of how I wrote one pass, you can see that I had to introduce new variables occasionally. It's like, oh, I didn't think of this. Oh, I didn't think of that, okay? Or the boundary condition, where I stop, I would go like, when I is greater than or equal to last, okay? Because last definitely is related to what I need to check against. And then I realized, oh, it's last minus 1 and not actually last. So there are refinements that I have to do as I continue to work on the algorithm. I did not come up with the algorithm all at once like that, okay? It took several iterations to get it right. So that is something that you can expect as well when you are going to move on to cisp300, where your professor will give you a problem to solve, okay? I need you to write C code to do blah, 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 blah. And first of all, you definitely want your professor to give you examples. Okay, so in addition to specification of what your program is supposed to do, it really helps if your professor can say, if this is the input, that would be the output. If this is the input, that would be the output. So even though your professor may not be giving you the Hungarian dance, okay, it would still be at least something that you can check against. Is my algorithm doing what it is supposed to? If I apply my algorithm to this input, do I get the output that the professor specifies? So that would be really helpful. Now, if your professor can also give you something equivalent to the Hungarian dance, which is basically like the intermediate steps, how to go from the input to the output, that would be even better. So you can at least ask your professor, okay? If the homework assignment doesn't have examples of input and outputs, doesn't give you examples of intermediate steps, you can ask your professor, what is the worst thing that can happen? The professor just says, now you have to work it out yourself. But it doesn't really hurt, right? But those are the components that you need in order to step by step make or construct your algorithm. So are we okay so far with that step? It's really difficult for me to teach how to design an algorithm because it's a process that is really inside my head that is difficult to describe. It's kind of asking a well-known artist and go like, so how did you paint that picture? The artist will be able to tell you exactly how to mix the color, okay, or how to get the proportions right and stuff like that. But the artistic side is difficult to explain. Why did I choose this particular scenery instead of the other one, okay? that becomes difficult to explain. So it's kind of the same thing here. So do you guys have any questions? No? Okay. So we'll do one more thing, at least a few more things today. On Friday, I will give you guys the practice exam, because next Wednesday is the actual final. So if I give you the practice final on Friday, that will give you the weekend to kind of study your material, and then Monday is the last lecture, so that you can ask questions regarding that material on Monday. Is that making any sense? Okay. All right. But before we do that, okay, it is my obligation to show you this. This is, every professor has access to this particular intranet, okay? And what I want to show you is what we call the curriculum of this particular class. Every single class has a curriculum. So we can look for the curriculum of not this class, but the next one. Do you know why? Because I need to make sure that you guys have at least enough material to move on to cisp 360. So we'll look up cisp 360. That's C and C++ programming. Right? Mm-hmm. They call it structured programming, but it's basically just C and C++. So this is cisp 360, Introduction to Structured Programming. So the programming language is not even a part of the title. So yeah. And here is the ARC version. Okay. And the portion that we need to pay attention to is how it describes the prerequisite of cisp 360. So let's see, where is it? Prerequisite justification, there we go. So let me magnify this, because this is the portion that is kind of important. All right, so there's a prerequisite justification. Basically, it's asking the question, why does cisp 360 list cisp 300 or 370 as a prerequisite? And that is important because I need to make sure that all of these points are covered. So we'll go through these one by one. Compare two methods of passing results using by reference parameters versus versus returning a value. So are we good with that one? By reference, we use that in the swap subroutine. And then with factorial and many other subroutines, we use a return value to specify, oh, this is the result of the computation that you asked me to perform. Next one up. Compare inline copy and paste coding with structured subroutine in terms of maintainability. I did not actually talk about this, but this is not technical. It's more of a best practice kind of thing in programming. Every time you copy and paste code, you have to ask yourself, can I turn that code that I'm copying and pasting into a subroutine? Okay? So I will use 2 minutes to explain why. Okay? First of all, if you just copy and paste, and let's say there are 20 places that you copy and paste into, okay? And then after that, you discover a bug of the code that you just copied and pasted 20 times. What do you have to do?
Fix it 20 times.
Fix it 20 times only if you can remember where you pasted it 20 times. What if you miss one of those 20 times? Yep, the program will still be buggy, right? Because you missed that one single copy that you did not fix. But if you use a single subroutine where all 20 places are subroutine calls or invoke statements to the same subroutine, how many times do you have to fix it? Once. Okay, well, that's the reason. So every time you copy and paste, try to use a subroutine instead. Okay. Synthesize a subroutine to abstract one or more similar blocks of inline code using local variables, parameters, and return values. I think we got that covered, even though I did not explicitly explain this particular concept. Define operators, including arithmetic operators. I think those are the ones that you already know, addition, subtraction, multiplication, that sort of thing. Comparison, less than, greater than, less than or equal to, greater than or equal to, and not equal to. And then logical operators, and or not. We got that. Differentiate control structures. Okay, in other words, do we know the differences between these things? Do we know how a conditional statement is different from a loop, and how a loop is different from a sequence? And do we know the difference between a repeat until, which is called a post-checking loop, versus a while do loop, which is a pre-checking loop? Can we tell the differences between those? Okay. Moving on. Deduce post-condition from precondition for control structures, including assignment statements, branches, and loops. I think we covered that. Okay. The pre and post conditions involving substitution and forget. Yep. Okay, we got that. Construct a trace table to emulate the execution of a program that utilizes variables, control structures, data organization, subroutines, and parameters. Yeah, we got that. So I think we hit all of the important areas of what your cisp360 professor is expecting. Is that okay? Are you guys feeling kind of comfortable, or going like, I don't think we are ready to move on? Because we lost a significant amount of time. Yeah, but that 2 weeks is more significant for a second 8-week class compared to a 16-week full semester class. Yep. So I think we're still good, okay? We are still good. The only portion that I really would like to have more time to spend on is how to synthesize a subroutine to abstract one or more similar blocks of inline code using variables, parameters, and return values. That is going backwards, okay? Because when you say, okay, I'm about to copy and paste, wait, text that do not copy and paste, use a subroutine instead. That means you're making a subroutine already. This one here, let me highlight which portion I'm talking about. This portion here is going back in time, or you're reading the code of somebody else. Okay, you go like, wow, I can find at least 20 places where a similar block of code was just repeating itself with minor variations. Okay, so in your mind, you now go like, there's a little tag talking in your head saying subroutines, 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 right? So now the question is, how do you look at those 20 pieces of code that are about the same but not entirely the same and say, how do I turn all of these into one single subroutine? Just call them with different parameters. That is the question. Do you guys understand what I'm talking about? So that really is, it's an abstraction, because what you're trying to do is you're comparing the instances for differences. Wherever you find differences, turn those into parameters. And that's why we need parameters in subroutines, is so that one single subroutine can take care of multiple cases where the subroutine is needed. Is that okay? I might even have that note available. So let me check to see if that is actually available. These are all the modules that I have written for various classes. Writing pseudocode subroutines. That might be it. I'm not sure. There's a lot of stuff like that where I write something and I cannot remember whether. Okay, this one is actually helpful because it actually talks about the process of writing a subroutine and differentiating when to use pre-checking and post-checking, but it's not what I was looking for. Writing and using subroutine VBA, Visual Basic. Subroutine using the toy processor. Nope. Control flow. So apparently I do not have that. Okay. Or maybe I called it differently. Okay, so I'm going to go back, when I go back home today, I'm going to look for that. because I vaguely remember writing something about it, but that was when I was still using a different LMS, so I might not have written that in this particular format. So that's the only part where, we are a little bit lacking. I did not tell you what the how to do that. How would you do it? Okay, first of all, can you notice, that a piece of code had been copied, pasted, and modified several times in the program? I think most of the time we can, okay, because it looks like that, right? You have a loop, there's a condition, to stay in the loop, there's a conditional statement inside, and then the structure is very close, okay, even though some of the constants, the numbers are slightly different, okay? So what you do, I really need to find that, is to try to make a single subroutine that can take care of multiple places where similar code appears. So that is a very useful technique because it can make your program easier to read in the long run, and it will also help to it will help to contain bugs. Can someone tell me what differentiates a good programmer versus a bad programmer? I think we talked about that already. Readability. Readability is one, but readability is only one of the measuring sticks that we use for something that is actually important. Efficiency. Okay, so when you talk about efficiency, I'll get to you. When we talk about efficiency, are we talking about how fast we can write code, or are we talking about the efficiency of the code that you're writing? Okay, that is important, but there's also the efficiency of how fast you can write code. Yep, go ahead. Debugging. Debugging, okay, very good. So there's a debugging part, okay? How much time do you think you spend on writing new lines of code as opposed to how much time you spend on fixing bugs of existing code?
Like 8 to 2, maybe 9 to 1.
9 to 1, which means 90% of the time you're fixing bugs and only 10% of the time you're adding something to a program. That sounds about right, okay? So from that perspective, debugging or knowing how to debug a program efficiently becomes one of the really important factors of being a good developer. Is that making any sense? Because you're spending more time troubleshooting than you're spending time writing new code. Okay? So debugging is a technique that, once again, is really difficult to teach. And you also need the right tools to do it. When you move on to the next class, depending on who is teaching cisp300, sometimes they do not talk about debugging at all. Okay? So what do you do when your professor doesn't teach you how to debug a program?
Google.
You can Google it, okay? You can Google it. So the first thing you need to know is to understand what is a debugger, okay? Okay, so I'm going to look up debugger first. And Facebook for developers, okay? JavaScript. Okay, we'll look up Wikipedia first, because the first question is, what is a bug? Trust me, all this discussion is leading to the process of debugging, but we have to know what a bug is. Yep.
It's an event that happens unintentional, or it's an unprogrammed event that happens, basically.
Okay. So there are different ways of looking at what a bug is, but the way that I look at it is a bug is a defect. Okay, it is a part of your program that is not correct. Okay. So how do you know there's a bug in your program?
Sometimes it will produce an error message when you attempt to run it.
That would be the lucky times. Yes.
Otherwise, it just doesn't work correctly, or that could be anything from a crash to a stop to
Okay.
just sitting there and not doing anything.
So all of those are symptoms of having one or more bugs in your program.
Yeah.
Okay. So once again, let's go ahead and kind of repeat all that stuff. Your program crashes. So when we say a program crashes, what does it mean? It doesn't respond, it just crashes out. In other words, the program stops execution way short of what it is supposed to do, okay? So it's crashing out. It can also give you an error message. And that is a very rare case where you feel this is my lucky day. My program actually gave me an error message that tells me something is wrong on this particular line. Most of the time, it doesn't happen like that. There's also the symptom of your program simply not doing what it's supposed to. So if you think about bubble sort, okay, if you implement it incorrectly, one particular way for a bug to show up is when it's all done, the array is not sorted. Or it's mostly sorted. Is that okay? So all of these are ways for a bug to quote unquote show up. They are symptoms of having at least one bug in your program. So let's say your program is not working the way it's supposed to. Oh, wait, hold on a second. Doesn't that mean that you have to know what your program is supposed to output in order to compare the actual output and say, oh, it doesn't match what I think the program should be doing. I think there's something wrong with my program. So this means in cisp300, in any programming classes, it is really important that you understand what the program is supposed to produce given a particular input. Ask your professor for examples. Okay? Give me some examples. If this is the input, that should be the output. If this is the input, that should be the output, and so on. Okay? That is really important because otherwise, sorting is easy, okay? But they're not going to give you a homework assignment and say, write a sorting algorithm. Why not? You can just look it up, exactly. You can look up at least 5 or 6 different sorting algorithms. So every sorting algorithm known to mankind under the sun is already on Wikipedia. So it makes no sense whatsoever to have a homework assignment that would just ask you, oh, give me a sorting algorithm. So your homework assignment is going to be involving something that Wikipedia has no algorithms as a reference. So if that is the case, it has to the output of a particular input is not going to be something that is easily specified, like, oh, this is a sorted array, that is supposed to be the output of this program. So it's important to ask your professor for examples. If this is the input, you perform these operations, that is supposed to be the output. Okay? So once once you know your program is not doing what it is supposed to, what do you do next? This is my favorite part because I get that question all the time. The question is, okay, so you wrote a program to solve a particular problem, but the output of your program doesn't match what you think it should be, or it doesn't match the specification of what your professor specifies. So what do you do next? Yep. Okay. So the most popular question that I get out of these situations is, Dr. Tech, my program doesn't work. Now,
It's not so much a question.
Okay, how about this? Why is my program not working? Okay? Yep, go ahead.
I would try to recreate that issue again.
Okay, so that's very good. Okay, recreating the issue. In other words, you are trying to find exactly what input is going to cause the program to give you a consistent erroneous output. So this way, okay, if this is the input, this is the output. Even though the output is incorrect, it is reproducible. So that's good, which means when you test your program, don't test it with just some random test data. Okay, because if you test your program using some random test data, it is difficult to reproduce exactly the same thing. So always use known input to your program. You test it systematically. If it doesn't work, you write down on a piece of paper or your computer and say, this input gives me an incorrect output of that. Okay? All the programming homework assignments on this, in this college is going to have a reproducible output. So we are not going to write any type of multi-threading program. There are no interrupts. All of the really big, bad concerns about, oh, the program only has one bug, but it has 20 gazillions ways of showing up, is not going to exist in your programming assignments, which is good. okay, because you don't want that. So once you know, okay, this input gives me an erroneous output of that, what do you do next?
Trace it.
Hmm?
Trace it.
You can trace it, but tracing using, when you have a large program, tracing can be very difficult. So now it goes back to how do you write your program? Yep.
I would insert, I'm forgetting what it is, but like
Assert statements?
I think so. Basically, well, I do print statements
Mm-hmm.
all over the place to see how the variables change down the program. And
Okay.
I think that's also unfortunate.
No, no, no. If you use print statements, that's actually not a preferred way of debugging a program, because one, your program can be outputting like thousands of lines of output, and becomes very hard to sort it out. Like where is my mistake, or when is my mistake first showing up? So the other way to write programs, okay, in a structured way, remember top-down design in this class? We start with bigger blocks and then we work on the smaller one. That's a good process to break a big problem into smaller programs, into smaller blocks. But when you're actually writing code, do it the opposite around. In other words, you break it down to the smallest chunk first, right? You write that chunk of code as a subroutine. You test that piece of code first. Okay? So top-down design, starting with something big, break it down into smaller parts, and then smaller parts and smaller parts, is a good way to start organizing your program, but it's a horrible way to debug a program. Because you cannot really run the program until you have all the pieces in place. So now you have a program that has 300 lines of code, and none of those lines have been tested. And when your program doesn't work, how many lines are suspects? 300 lines. Not good, okay? So what you want to do is to break it down into small pieces until each small piece is about 10 to 20 lines, okay? And then you test that piece of code using some test data. If it works, then it's good. If it doesn't work, how many lines are suspects? 20 lines. It's a lot easier to debug a subroutine that only has 20 lines than an entire program that has 300 lines. Is that making any sense? So when you write your program, when you develop your program, you actually do, I personally do it in a bottom-up way. Okay, I look at the smallest pieces first, implement all of those things, test those things independently. Once it works, then I take a step back and go like, okay, assuming these blocks are working, what is the next bigger block that I can create out of these smaller blocks? Okay, so that's a technique where you can contain bugs, because if you're only adding, so let's say you have 3 blocks of code that you have already written and they're tested, and you're now constructing the 4th block of code that makes use of those 3 blocks of code. Something is not working. Well, it has got to be the new code, okay? Because those 3 smaller blocks have been tested already, assuming you tested those thoroughly. So that's why it is important to write code develop code in a backward manner. You start with the smallest blocks first. Then you test each block before you create larger blocks. Uh-oh, my computer just went to sleep again. There we go. Is that okay? So if you use this approach, there are more tools, okay, that your professor is unlikely to tell you. Does anyone know what is revision control? Revision control.
Isn't it like GitHub?
Yes. So what is GitHub?
So version control.
Version control and revision control are the same thing, okay? But what does it do? Okay, go ahead, Izzy.
It basically, you can extract apps from it or programs from it to install onto your system or
Okay.
tests, basically, like you're pulling from like a repository.
Yep. The term is repository. Yep. Okay, that's from the standpoint of you want to install something. But from a developer's perspective, as a student in computer science, taking a programming class perspective, from that perspective, what is GitHub? What is that going to buy you? Hmm?
So the save point.
A save point, exactly. So let's say you got the program up working up to a certain point. Okay, you say, okay, I have tested my code. These are the test cases, and they all work out. Okay, so you know you have done a certain portion of programming correctly within your program. So what you do is you check it in to the repository. Okay, it's usually just one single command, like get, update, blah blah blah. Okay, I cannot remember the exact command, but it's a simple command. So what you're doing is you're creating what we call um, a restore point. Okay, if you use the Windows update analogy, it's a restore point. Okay, so now the restore point is a particular version that you're tracking in using GitHub. So let's just say that you took one too many pills of a flu medication, and then you decided, oh, I need to finish this program, even though I'm not really in the best form. And then you code it, and you wrote like 20 lines of code, not in your best shape, okay? And then the next day, you realize your program is not working anymore. Okay, what are you going to do? You compare. You compare your program with the last saved point. So you look at the differences, okay? What lines did I add to the program? What lines did I remove from the program? What lines did I change in the program? Because if your program was working up to a certain point, and now it's not even working in those particular test cases, it had to be because of the lines or the changes that you have made. Revision control, GitHub is one of those tools, gives you a very visual way to compare versions of your code. As long as you remember to check in your code after you test a certain portion and go like, okay, I know this is working up to at least this point, you check it in, it will give you that ability to compare your current version of the code with the version that is known to be good up to a certain point. So if your program suddenly stops working, it makes it easier to go back in time and go like, oh, I see that line of I++ doesn't belong there. Now I know. But it makes it easier to locate the changes. Because as your program gets larger and larger, let's say your program gets to become like 300 lines, okay? And you make 10 lines of changes. And then now the program is not working at all. It's just crashing. It's much worse than what it was before. Without revision control, unless you have photographic memory, where did you make those 10 changes? You may not remember, right? But if you have revision control, then the software will help you. It will color code it and say, this line was inserted, this line was deleted, this line was changed. It will highlight it for you. So it makes it very easy to spot within the 300 lines of code which 10 changes you have made. Then you can go back and go like, oh, that was stupid. And undo that, okay? So those are really useful tools, okay? Because if you don't use GitHub or revision control tool, the closest you can get is to save the file under a different name, okay? Which is fairly common, okay? But if you save it under a different name, most people just use a sequential number like bubble sort 1, bubble sort 2, bubble sort 3, and so on. What does bubble sort 4 mean? Did it mean that one pass is already known to be working and you're working on bubble sort the caller itself, or what? But if you use revision control, it gives you a chance to comment. Every time you check in your code, you can write some comments and say, I'm checking in this project because I have tested it. One pass is already working. Next, I will be working on bubble sort. Okay? So that is really helpful. Yep, go ahead.
I just had this like massive game mod I was developing at one point, and I had every copy of it on, just my computer, and that's, it's a massive project that references hundreds and hundreds of files, and so the entire game, like that's 8 gigs, is on my computer multiple times. And you obviously can't keep all of those.
Yep.
So you start deleting ones, and you don't know ones you deleted. Like, you just can't have all that stuff on your personal computer. It's messy.
You start to lose track of things.
Especially if you start trading things between the two of them. It's like, well, now you've screwed everything up. Like, the best
Mm-hmm.
and get them that way. But like, yeah,
Okay,
same
so
principle.
I got one more point to make. We got about 4 minutes left. Okay, do you think GitHub is only going to helpful to get you through college, and then after college it's like, oh, I don't need that anymore. Woohoo!
No, it's not gonna waste up your portfolio work.
It is a very big item on the portfolio when you're looking for that very first job. Being a student or a graduating student, and you can list and say, I know how to use GitHub. I know. Why? Why do you think GitHub is so useful? Besides, just revision control, it serves one more important purpose that really doesn't apply to your homework assignment. Yep.
You could basically, it's like a Google Drive for computer software developing, just because you could have a large project where one person could be working on the
Yep.
GUI, one person could be working on logic.
It's a collaboration tool.
Yeah.
So it's a collaboration tool on top of revision control. So that means, in the real world, do you think you'll be the only one working on a particular project? No, you can have 5, 10, 500 people working on a particular system at the same time.
So companies use GitHub
Big time, big time.
Literally everyone uses
I
GitHub.
cannot,
insanely.
I cannot imagine any developer in the commercial world not using GitHub or something like GitHub. So GitHub is a huge item on the resume. Okay, if you know how to use GitHub, especially when you use it in a collaborative environment, when you're working on a project with several people, and you guys know how to manage the project, and say that, okay, I'm working on the GUI side, but I'm not gonna check in my code until I have tested this code. And then the other side goes like, okay, whatever update you have pushed to the server, I'm gonna incorporate it into my code so that I have the latest working version of your code. That type of management, that type of collaboration is worth a lot of points when you're looking for that first job as a developer. So GitHub is not something that is like, oh, okay, well, tech says it's useful, my classes, I'll learn it, but after graduation, I don't need that anymore. No, after graduation, you need it more than before you graduate. Yep.
I mean, my partner gets calls for jobs, just from people who have seen their